Hi, my name is Brandon, and this is my report for Lab 2, Lines of Charge. The purposes of this experiment were to estimate the charge on a charged piece of tape using a model on Python, where we modeled the charge tapes as lines of charges. We also wanted to determine the magnitude of the electric and gravitational forces acting on the tape. The main physics principles in this experiment were the equation for the electric field of a point charge, Coulomb's law, which allows us to calculate an electric force, and finally, Newton's second law, which we use to calculate the gravitational force. The results we found in this experiment are that the charge of the tape is equal to around 1.78 times 10 to the negative 8 coulombs, and the magnitude of the electric and gravitational forces acting on the tape are 1.764 times 10 to the minus 3 newtons. In this report, we will first cover the experiment and the results we got from it. Next, we will cover the code, the model, and the results from that. And finally, we will address some final questions. First, let's go over the procedure of our experiment. The first step was to create pieces of charged tape. To do this, we attached one piece of tape to a flat surface. Then we attached another piece of tape on top of the last one and quickly ripped it off. This created a charge on the tape. Then we stuck one tape onto two vertical supports, as shown on the drawing here. Then we created another piece of charged tape and brought it underneath the first one. Since both tapes had the same sign of charge, they repelled each other. And we held the lower piece of tape at a distance at which the upper tape was floating and stationary. Finally, we measured this distance between the two pieces of tape, and we also measured the dimensions of the upper piece of tape. We found that the tape measured 18 centimeters by 2.7 centimeters. And the distance between the two pieces of tape was 1.5 centimeters. With this data, we were able to do certain important calculations. First, we calculated the mass of the tape by multiplying the length of the tape by a mass per length value which we were given. We found that the mass was 1.8 times 10 to the negative 4 kilograms. Using this mass, we were able to calculate the gravitational force. Newton's second law tells us that the force acting on an object is equal to its mass times its acceleration. In this case, the acceleration is the gravitational constant for the Earth, which is 9.8 meters per second squared. We found that the magnitude of the gravitational force is equal to 1.764 times 10 to the negative 3 newtons, and pointing downward in the negative y direction. Once we know the magnitude of the gravitational force, we can calculate the magnitude of the electric force. Since we know that the tape is stationary, then we know that there is a zero net force acting on the tape. Assuming that the only two forces acting on the tape are the electric and gravitational forces, the magnitude of the electric force must be equal to that of the gravitational force, but pointing upward in the positive y direction. Now let's go over our model. For this model, we made several assumptions. First, we treated each tape as a straight line of point charges, as shown here. We also assumed that each strip of tape had the same amount of charge evenly distributed on each point charge. Finally, we assumed that only gravitational and electric forces were acting on the tape. We ignored, for example, the resistance force of the tape stuck to the supports. For the code, we started with an estimate for the charge on the tape, and we used the value we found for Lab 1. Then we calculated the electric field of each point charge on the upper tape due to each point charge on the lower tape, using the equation for the electric field of a point charge. So for example, for this point here, we calculated the electric field due to every point charge on the bottom, and so on for the rest of the points. Then we calculate the total electric force on the upper tape due to the lower tape using Coulomb's law. To do this, we multiplied the electric field of each point by the charge on each point, and then added them all together. Finally, we compared the magnitudes of the electric force and the gravitational force, and we varied the estimated charge on the tape and repeated until the magnitudes of the forces matched. Now let's take a look at the code. First, we define the constants used in the code. Next, we define the observed values, which are the mass and the estimated charge. Next, we define a function, which calculates an electric field based on a charged particle and an observation location. Next, we define another function, which creates the line charges. Then we create both charges at their respective positions. Finally, we iterate across every point charge and calculate the electric field and the electric force. We also draw arrows to represent the relevant forces and fields. And we print out important values at the end. The red and blue represent the two pieces of tape, which are both divided into different point charges represented by the spheres. The green arrows represent the electric field on each of the point charges of the upper tape. The white arrow represents the electric force, and the yellow arrow represents the gravitational force. We can see that using a value for the charge on the tape of 1.78 times 10 to the negative 8 coulombs, the magnitudes of the electric force and the gravitational force match. Therefore, this is the estimate for the charge on our tape. Now let's go over some final questions. In Lab 1, we used a single point charge model to estimate the charge on the tape. We found that the charge was equal to 6.64 times 10 to the negative 9 coulombs. In this lab, using the line of charge model, we found that the charge was equal to 1.78 times 10 to the negative 8 coulombs. This means that the charge from Lab 2 is around 2.7 times larger. These values differ because in Lab 2 we're considering multiple points rather than a single point. The electric fields from points on the edges which are farther away will be smaller and have an x component. Because the electric fields on the edges are smaller, the overall charge must be larger to compensate for this. The estimated charge we found in this lab is more accurate because we used a line of charge model rather than a point charge model, and we're making less assumptions. In conclusion, we were able to accomplish the objectives of estimating the charge on a charged piece of tape using a model in Python. We modeled the charge tapes as a line of charges. Finally, we determined the magnitudes of the electric and gravitational forces acting on the tape. We successfully applied the physics principles of Coulomb's law, the equation for the electric field of a point charge, and Newton's second law. Our final results are that the charge on the tape is equal to around 1.78 times 10 to the negative 8 coulombs, and that the magnitudes of the electric and gravitational forces were both equal to 1.764 times 10 to the negative 3 newtons, and pointed in opposite directions.